Hi, I'm Professor Goins. In this video, I'm going to look at one of the convergence tests that you will learn about in your Calc 2 class called the ratio test. All right, so let me motivate the theorem as follows. For an infinite series, let's say I've got the sum n equals 1 to infinity, so I have this infinite series. Let's consider the following limit. If I take the limit of the ratio of consecutive terms, so that's what an plus 1 over an means, is I take the limit of like the second term over the first term, and then the third term over the second, and the fourth over the third, so on and so forth. So I'm taking the consecutive terms here, taking the ratio, and taking the limit of all of those. All right, so in particular, what can I say if the limit happens to be 2? Could be any value, but let's just see what happens if it's 2. So in other words, the limit as n goes to infinity of that ratio is equal to 2. Well, that means that for very large values of n, right, this ratio is eventually approximately 2. So I can say that for large values of n, this ratio is essentially 2. Well, I can rewrite this. If I multiply both sides by an, that means that I've got an plus 1 is approximately twice an. That means that each term is approximately double the previous term. Therefore, 2an would be bigger than an, right? If I double something, again, I'm assuming, I should have said this at the beginning, assuming that an is positive. Then 2an would be bigger than an, so I keep getting bigger each term. Well, if the terms keep getting bigger, right, if I keep doubling or getting more than twice the previous term, then an is an increasing sequence. And that means that the series is divergent. Remember, the divergence test says that this series, if it converges, then the an terms have to go to 0. That doesn't mean that it's convergent, that those terms go to 0, but in order to be convergent, that's one of the characteristics of the terms have to go to 0. So if I know they don't go to 0, then it's definitely a divergent series. So what I want to do is we're going to explore this limit right here, okay? And we can see right here through this discussion, in the particular case that the limit was 2, then we have an increasing sequence, therefore it's divergent. Okay, let's take a look at the statement of the ratio test, and then let's use it for some examples. If an is bigger than 0 for every n in n, so in other words, this upside down capital A, as a reminder, is the universal quantifier. It just stands for every. This means as an element of n, this capital N with a double bar on the side means positive integer. So this is a shorthand way of saying for every positive integer. In other words, every term. Okay, so if every term is positive, and I define rho, this Greek letter rho, to be the limit at infinity of this ratio, then when I compute that limit, depending on the value of rho, we have a couple of conclusions here. If the value of rho, meaning this limit, is between 0 and 1, then the series converges. If the value of rho is bigger than 1, then the series diverges. In this discussion over here, this was rho, right? So this was the specific value of rho, and we saw that it diverges. But rho could be anything bigger than 1, then the series will diverge. In the third case, well, what if rho is exactly equal to 1? If it's exactly equal to 1, all that says is that this particular test is inconclusive. It could converge or diverge. That means you just have to apply a different convergence test to it. So let's see for some specific examples of some specific infinite series how the ratio test works. All right, so let me clean this up and set up some infinite series. So use the ratio test to determine convergence or divergence, or perhaps we'll get an inconclusive, but attempt to determine if the series is convergent or divergent using the ratio test. Let's list 3 series here. Part A, let's look at the infinite series n equals 1 to infinity of 5 to the n over n factorial. Part B, let's look at the sum n equals 1 to infinity of 1 over n. And for part C, let's look at the sum from n equals 1 to infinity of n to the n over n factorial. So A and C are similar, and that part A, I've got 5 to the n, part C, I've got n to the n. All right, so let's use the ratio test. Okay, solution. Part A, again, I'm going to compute the limit at infinity of the ratio of consecutive terms. Okay. So remember that an is the expression inside the summation. So this right here, 5 to the n over n factorial, is an. So an plus 1 means I'm going to replace that index variable with n plus 1. Okay, so what that means for this first example, an, let's do the an first, that would be 5 to the n over n factorial. There's your an. An plus 1 would be 5 to the n plus 1 over n plus 1 factorial. So then let's simplify that expression and evaluate the limit. All right, so I can flip and multiply this to make that one fraction bar. So this equals, we've got 5 to the n plus 1 over n plus 1 factorial times n factorial over 5 to the n. Properties of exponents with the 5 to the n plus 1 and 5 to the n, the bases are the same, so I subtract the exponents, leaving a 5 to the first on top. And then I've got n plus 1 factorial and n factorial. So remember that n plus 1 factorial means n plus 1 times n minus 1 down to 3 times 2 times 1. So if this is my denominator, notice I'm going to cancel n factorial, meaning n minus 1 all the way down to 1. So what's going to happen is all of this will cancel from your denominator, leaving just the n plus 1. So I've got the limit at infinity of 5 over n plus 1, which of course is equal to 0, and therefore using the ratio test, if my value of rho is equal to 0, that says that the series is convergent. So I know the series in part A is convergent. For part B, all right, limit at infinity, ratio of consecutive terms, and in this case, an is the expression inside the summation, so an is 1 over n, which means an plus 1 would be that expression where I replace the index variable n with n plus 1. That gives me 1 over n plus 1. Just like the last example, part A, we flipped and multiplied, so let's do that same thing here. Okay, limit as n goes to infinity, so I would have 1 over n plus 1 times n over 1, meaning I'm taking the limit of n over n plus 1, and this limit is equal to 1. If I look at my ratio test statement over here, rho is equal to 1 means that the test is inconclusive. So the ratio test is inconclusive for this particular infinite series. Now, that's a pretty common series that you'll see in your Calc 1, or I'm sorry, your Calc 2 class. So this is the geometric series, and I know that that's divergent. One way that you can see that it's divergent is to use the integral test. So you may have seen the integral test before, but anyway, that is definitely a divergent series, but the ratio test doesn't know that, okay? So this is, again, an example of an inconclusive test where it does actually diverge. And it can also happen where the series converges as well. Finally, let's look at the series for part C. Again, limit at infinity, ratio of consecutive terms. Again, sometimes I think it's easier for students to put in the an first. So let's do the denominator first. That would be n to the n divided by n factorial. This is an, so an plus 1. I would replace all three of those n's with n plus 1. That would give me n plus 1 to the n plus 1 over n plus 1 factorial. Okay, so this one's a little bit messier. Let's take a look at how that will be computed then. So this is the limit at infinity. So just like the previous ones, let's flip and multiply, see what we get. So n plus 1 to the n plus 1 over n plus 1 factorial, and then I would have n factorial over n to the n. Okay, so we see that we can, first and foremost, n factorial over n plus 1 factorial. I can cancel n plus 1 factorial. I can cancel everything after the n plus 1. So this would give me n plus 1 to the n plus 1 over n plus 1, because the n factorial and then the factorial part of this cancels, where everything below n plus 1, which would be n minus 1, etc. That's exactly n factorial. And then I also have n to the n. I'd like to leave the statement of the ratio test up there, so let's go ahead and start back on this side. All right, so let's see what we have here. N plus 1 and n plus 1, the bases are the same, so therefore I can combine the exponents, and that would leave me with a factor of n plus 1 to the n on top. So I've got n plus 1 to the n over n to the n. Exponents are the same, so I can use that common exponent for the bases, and that would give you the limit as n goes to infinity of n plus 1 over n to the n. Inside the parentheses, I can separate the fraction. That would give you the limit at infinity of 1 plus 1 over n to the n. And that limit hopefully looks familiar. That's the definition of E. So this is this limit is equal to the natural base, E, which of course is bigger than 1. The limit is bigger than 1 means that the series diverges. So therefore, for part C, we know that that infinite series is divergent.